All right, welcome to the video on the limits and continuity test review. We're going to go through each problem one by one. Start with problem number 1. So it says on problems 1 through 6, evaluate each limit. So problem number 1 says the limit as x approaches -1 of negative x cubed plus x squared plus 4. So we're trying to figure out as x gets closer to -1, what is the y value getting closer to? We can see there is no negative or plus sign right here, so this is a two-sided limit. And generally speaking, when you're trying to evaluate the limit, what you do is plug the value in, and if you get an answer, you're good to go. If you get an error or an issue, then you try to work out the problem. So here we go. So let's plug in -1. So I'm going to take -1 cubed plus -1 squared plus 4. -1 cubed is -1 times a negative is +1. -1 squared is +1, so we're going to add 1 plus 4. 4 plus 1 plus another 1 is 6. So we got an answer out. We didn't divide by 0 or nothing, other issues like this. So that is simply going to be the answer to our limit. Our answer is 6. And if we were to graph that, you could see that as we approach -1, the output value would get closer to 6 from both sides. All right, problem number 2. This one is the limit of e to the x plus 5 as x approaches -infinity. So this is a one-sided limit, and we remember with our one-sided limits, it is okay to have an answer of either positive infinity or negative infinity or simply just some other number. That's okay. On the two-sided limits, like we just did on problem number 1, these positive and negative infinities would not be appropriate answers. We would just say it does not exist. But on this one, it's okay. It is okay to have to have one of those answers. All right, so let's take a look at this. Same idea with number 2. We just kind of want to plug our limit in. Now it's kind of hard to plug in a negative infinity. So just imagine we're plugging in a very large negative number. Okay, so it's very far away from 0. So e to a very large, some very large negative number, plus 5. As we look at this, all right, we have a negative in our exponent. We can deal with that. It's hard to evaluate, at least for me. I don't like looking at it, evaluating this with a negative in the exponent, but we can change that. Properties of exponents allow us to put the exponent and its base below a division sign, so or the denominator of a fraction. So it would be something like this. And we have to have a 1 on top because it's not 0 over this. It's going to be 1 over that. You can think of this as being times by 1, right? And so I'm moving this part of it down to the bottom, not the 1. Anyways, and then we got the plus 5. So now let's think about this. As e gets raised to a power, now it's positive power, e to some positive power is going to be a large number. The bigger this number gets, the larger the value of my denominator gets. So I'm getting 1 divided by a ridiculously large number. It's getting larger and larger and larger and larger. So if I take a 1 item and I try to divide it by a large number, I'm always going to get an answer out, but the answer is going to get so minute, so small. It's going to get closer and closer and closer to 0. So let's just treat it as a 0. Let's just pretend, okay, yeah, let's say we could get 0. Because we're trying to find the limit. What are we getting closer to? So we'll just treat this as 0. So I have 0 plus 5 is 5. And that would be our limit. So we have this equation right here has a horizontal asymptote at 5. As we went to -infinity, so it looks something like this. So here's our graph. 1, 2, 3, 4, 5. It's going to have horizontal asymptote right there at 5, and it's going to look something like that. And as you can see, as we go this direction, as it approaches -infinity, is getting closer and closer and closer to that value of 5. All right, problem number 3. Let's scroll down just a little bit so he's kind of more in the middle of our screen. There we go. All right, so problem number 3. We are trying to evaluate the limit of this function right here as x approaches -3 from the left, or from negative infinity, if you want to think of that as that way. So from the left. We don't care about the right, just the left. Well, with one-sided limits, as this one is, we do the same thing we've been doing on the other problems. Whenever you try to evaluate a limit, just plug it in, And if it works, great. If it doesn't, then we have to do a little bit more work. So let's try plugging -3 into this. So we're going to have -3 plus 1 divided by -3 squared plus, whoa, that's a 6, not a 3. I was about to write 3 plus 6 times a -3 plus 9. All right, so we got -3 plus 1 is -2 divided by -3 squared is a positive 9. 6 times -3 is -18 and plus 9. And as we look at this, 9 plus 9 is 18. So if I subtract 18, I get 0. So I end up getting -2 divided by 0. So we have a number other than 0 divided by 0. That means that what's happening at -3 is an asymptote. So that means the limit, the two-sided limit, does not exist. However, since we're just dealing with a one-sided limit, similar to problem number 2, we won't have an answer of does not exist. We'll have an answer of either positive infinity, negative infinity, or a number. The number's already been ruled out because we have an asymptote going on. So our answer is either going to be positive infinity or negative infinity. So we just have to decide, okay, which one is it getting closer to? Let's take a quick look at a number line. So here's 0, here's -3, okay, whoops. And as we look at this, we're looking at as x approaches -3 from the left, so from this direction over here. Okay, so we're approaching -3 from this direction. All right, so we know that it is either going to go, so we know there's an asymptote right there. So we know it's either going to go up forever or down forever. The question is which one. So we want to imagine, or you can actually do it, but we want to imagine plugging a number in very, very, very close to -3, just to the left side of -3. And I mean like really close. I mean, I think of -4 being way over here. So we're not like plugging in -4, -5, or -6. We want something very, very close to -3. So for instance, let's just plug in, let's plug in negative like 3.00001. All right. So we've got -3.00001 plus 1 divided by, now here we got a problem. We could try plugging that in, but that's going to be very difficult just for us to figure out, what happens when you square this. Our whole goal here is to figure out, is this final value going to be positive or negative? I don't care what the actual number is, but it's going to be kind of difficult to do the way it's written. So actually what we want to do first is factor this. So let me do this. Probably should have done that first, but that's okay. So let me do this right up here. So we've got x squared plus 6x plus 9. And this will factor to x plus 3 times x plus 3. Okay, so as we come down here, if we plug in -3 into that, or -3.001, we have -3.0001 plus 3 times -3.0001 plus 3. All right, so now let's evaluate this. If I have a -3.001 plus 1, so a number slightly to the left of 3, plus 1, that is going to result in a negative number. Okay, I don't even care what it is. I just care if it's positive or negative. So here, the numerator, we're going to have a negative number. Okay, so that's the negative number. Here's my division sign. Down here, I've got -3.001 plus 3. Now that plus 3 is not quite big enough to make this number go past 0. So we're going to end up with a negative number from there. This is the exact same thing, so we'll have a negative number from there. So we have two negatives on the bottom. They are being multiplied together, so that's going to result in a positive. So I actually have a negative divided by a positive. A negative divided by a positive number is a negative number. So our answer to problem number 3 is -infinity. It's going down forever. And I've just used up a lot of space. We'll just put it right here. -infinity. All right, problem number 4. Let's come over here and look at this thing. We've got the limit as x approaches infinity. So once again, this is technically a one-sided limit, so it is okay to have an answer of positive or negative infinity or just simply a number. Our answer will not be does not exist. Okay, so we're looking at the limit of this function as x approaches positive infinity. All right, so similar to the ones we've done before, we'll try plugging in a number. With infinities, it's kind of fun. You just kind of imagine plugging in a very large positive number. So we've got -3.001 3 times some very large positive number. I'm just going to put positive number. That's squared. Divided by some very large positive number squared plus 4. All right, so let's think through this a little bit. In the numerator here, we have some positive large number squared, right? That's going to be a huge number. That square does a lot of stuff for us, right? It makes this number very, very large. And then I'm going to times it by 3, and that does, it triples it. That's not insignificant, right? On the bottom, and so basically on the top, I get we have that negative sign already, so we're going to have this. We have 3 times a very large number. Okay. On the bottom, we have that big number squared again. It's going to give me, if you notice here, it's going to give me that same very large number. So on the bottom, I'm also going to have that very large number, and those two values are going to be identical because they're just the number we started with being squared. But then I'm going to add 4 to it. So if you think about this very, very large number, if I add 4 to it, adding 4 is not going to change this number by much. It is going to change it a little bit, but not very much at all, like very insignificant. So we're talking about like the number of grains of sand on a beach, and I throw 4 more pieces of sand on the beach. Did the beach increase in size? Yes. Did it make much of a difference? No. Okay. But if I had, all those grains of sand on the beach, and I times that by 3, I had 3 more groups of sand that same amount. That does make a big difference, right? Anyways, so that plus 4 doesn't really do much. So if we look at this now, we have 3 times that very large number divided by that same very large number. Those basically just cancel out. And we are left with -3. So -3 is our answer. It is a horizontal asymptote. We have a horizontal asymptote as x approaches infinity. Now, one other way to look at this problem is we have a polynomial divided by a polynomial. So there is another way to look at this. We notice that the degree of the numerator and the degree of the denominator are the same. And so that tells us that there is going to be a horizontal asymptote. And one way we can evaluate that is we just take the leading terms, and don't forget that negative sign out front because that'll be important too. But we just take the leading terms and then we simplify, and the x squareds cancel out, and we're left with an answer of -3, which is essentially what we just did down here. We just kind of, actually thought through it a little bit more. But that's what you could do if you had the same degree. If the degree on top had been bigger than the degree on the bottom, so if this had been like 3x cubed instead of x squared, then the answer would have been negative or positive infinity, depending on which way we were going. If the bottom had been larger, so if this had been a 3 and the top had been a 2, if the bottom had been growing faster than the top, this would have gone to 0. All right, so we'll probably see that in a future problem. Okay, problem number 5. The limit as x approaches 1 of our function, this guy right here. Okay, so same as always, when we evaluate a limit, the first thing we want to do is plug it in. So let's plug 1 in. So we get that negative. We get 1 subtract 1 divided by 1 squared minus 1. So 1 minus 1 is 0, 1 squared is 1, and 1 minus 1 is 0. So our answer comes out to be 0 divided by 0. So that tells us, because we have 0 on top and on the bottom, we have the potential for an x value of 1 being a whole rather than an asymptote. So let's factor this thing and see if we can fix the problem. So now we came across a problem. We plugged it in. We have an error. We're dividing by 0. That is a problem. So we have to do a little bit more work now. So one thing we want to check to see is if this is actually a whole. And the way we do that is we'll factor and see if we can get rid of that problem, dividing by 0 on the bottom. So let's see. The top's already factored. So we do this. This is kind of a second step. We'll do this in a different color. The top is already basically factored, x minus 1. The bottom is x squared minus 1. That's the difference of squares. So you can go ahead and factor it. Or if you know your difference of squares rules, this is going to factor to be x minus 1 times x plus 1. And from there, we can see that this guy right here, this x minus 1 on the bottom, he is our problem. He is what's causing us to divide by 0. It's okay to have 0 on the top, but the 0 on the bottom is the problem here. And because if we plug 1 into this, we get 1 minus 1 is 0, and the bottom goes to 0. Well, fortunately, we have that same issue on the top, so those can actually cancel out, leaving us with negative. We need something still on the top, so we'll put 1 on the top, x plus 1 on the bottom in the denominator. So now if we now that we fixed the issue, that was the problem right there. Now that we fixed the issue, let's try plugging it in again. So we plug 1 in and we get negative 1 divided by 1 plus 1. 1 plus 1 is 2, so our answer is negative 1/2. So this problem right here, we have a horizontal I take that back, sorry. We've got a hole at positive 1. So this is basically what this would look like. So here's positive 1, here's negative 1. Okay, here's negative 1/2. So we have a hole right here. And I don't know exactly what this problem looks like, but let's just I don't know which direction I'm supposed to be going, but it would look something, you know, like that maybe. Okay, where you got that hole right there, that's what's happening. So the limit still exists, coming from the left, coming from the right, still equals negative 1/2, but you can't evaluate it at 1. All right, our last of our limit problems is problem number 6. The limit of this function as x approaches 3. So once again, let's just plug it in and see what happens. So we've got negative, this is a two-sided limit, by the way, 3 minus 2 over 3 squared minus 5 times 3 plus 6. So on the top, we are going to have 3 minus 2 is 1. On the bottom, we've got 9 minus 15 plus 6. Well, 9 plus 6 is 15. Subtract 15 is 0. So we end up getting, from this problem, we get negative 1 divided by 0. So we are dividing by 0. That is a problem. This is a two-sided limit. So right here, since we have a number other than 0 divided by 0, we know that at 3 there's an asymptote. Okay, so we know that at 1, 2, 3 there is an asymptote right there, which means the limit, the two-sided limit, cannot exist. It doesn't even matter if on both sides of the asymptote they're both going up to the same place, which I don't know if they are in this case. But even if they were going both up, they're neither side, the left nor the right, are approaching the same value. They're just going in the same direction. They're both going, in this instance right here, they're both going to positive infinity, but they are not going to the same value. Therefore, the limit cannot exist. Now, I don't know if that's what the graph looks like, but it could be, maybe one side's going down or something like that. And we could take the time to figure it out, but we won't. But especially if it was going opposite directions, then you know that it's not, it doesn't work either. So anyways, our answer to this problem is does not exist. If this had been a one-sided limit from like the left or the right, then yeah, we would go through and figure out which direction it was going. But since it is a two-sided limit and two-sided limits do not exist at asymptotes, we don't have to worry about it. I'm just going to erase those because I don't even know if that's what it looks like. All right, that takes care of number 6. Okay, problem number 7 says let f be the function defined below. So we got a piecewise function. For what value of k is f continuous at x equals 2? Okay. Well, if we remember our rules for continuity, there was 3 things that have to be true. The first thing is the limit as x approaches the x value that's in question, in this case 2, as x approaches 2 of our function has to exist. Okay, that's the first thing that has to happen. Okay, the second thing that has to happen is f of the x value that we're looking at. So evaluating our function at 2 has to be defined. You have to get an answer out. Okay, and then finally 3, whatever our value of our limit is, so the limit as x approaches 2 of f of x, whatever that value is, that has to be the same thing as where it's defined at, f of 2. So those 3 things have to be true for our function f to be continuous. So let's check out our limit here. So to evaluate a limit, let's see, we've got, let's do it right here, the limit as x approaches 2 of our function f of x. So we want to evaluate the limit as x approaches 2. Well, similar to 1 through 6, what we do is we just plug it in. So as x approaches 2, well, since it's a piecewise function, it's kind of hard to just plug in. We'd end up getting this 4k, well, yeah. Let's do it. Let's do this. Let's do one, since it's a piecewise function, let's do from the left and let's do from the right. And remember, if the limit's going to exist, these two values have to equal each other. So let's see, if we plug in 2 from the left, these are going to be numbers that are represented by numbers that are smaller than 2. So I look at my restriction on my piecewise function. I want the one that tells me about numbers that are smaller than 2. Well, this one right here is only for values of 2, so that's not going to help me. This one right here is for values smaller than 2, and happily enough, it's also for values larger than 2. So we're going to use this equation right here. Right away, I can tell when I plug 2 into this equation, I'm going to get 0 on the bottom. So let's not even bother plugging 2 in. Let's just go ahead and factor this thing. So let's see, let's do this in a different color. Let's factor the top. So we've got, you can go ahead and factor it the way you want to factor it. I'm going to factor it the way I want to factor it. Let's see, we need a 2 there, 1 there, we need a negative and a positive. Negative 6 plus 1, that works, there we go. All right, so that's the top factored. On my bottom also has an x minus 2 on the bottom. So this is the problem child right here. If I plug a 2 into that, right, I'm going to get 0 on the bottom. So that eliminates that right there, and then I'm left with 3x plus 1. So if I plug 2 in to 3x plus 1, I get 3 times 2 plus 1 is 7. Okay, so my left limit over here is 7. Well, my right limit, I'll plug it 2 into the expression of my piecewise function that represents values larger than 2. Well, guess what? It's the exact same equation. So I'm going to do the exact same stuff. I'm going to end up getting a value of 7 out. So my left-sided limit is 7. My right-sided limit is 7. They're the same. So my actual limit does exist. The limit as x approaches 2 of our function f is equal to 7. The limit has to be 7. All right. Is f of 2 defined? So let's see, f of 2. If I plug 2 into the function, what do I get out? Well, look at my restrictions. Okay, the bottom equation is for when x equals 2. You use this one when x is equal to 2. So I plug 2 in for x over here. There is no x to plug in, so that means my answer is just this. When I plug in 2, I get out 4k minus 5. So my f of 2 is defined. I get out an answer. So my limit exists, f of 2 is defined, therefore all that has to be true is this has to be true. My actual limit, 7, has to equal the value I get when I plug 2 in, or in this case, 4k minus 5. And now I've got my equation, I can solve for k. So we're going to add 5 to both sides. 7 plus 5 is 12. And divide both sides by 4. 12 divided by 4 is 3. So the value of k that makes this statement true, that kind of plugs that hole, right? We're going to have a hole at x equals 2. Okay, the value that plugs that hole is plugging in 3 for k. Will give me a hole plug for that hole. And that makes my function continuous at x equals 2. All right, let's take a look at problems 8, 9, and 10. So problems 8, 9, and 10. Use the following piecewise function to answer 8 through 10. All right, that's simple enough. All right, what is the value of f of 1? So we are plugging 1 into our function f. So we have to make sure that we plug it into the right expression. So we look at the restrictions over here. This one is for x values less than or equal to 2. In fact, this is probably going above and beyond what we need to do, but that's okay. I'm going to draw a little number line so we can see. So here's 0, and here is 2. That's the one we're looking at, right? So we've got this expression right here. I'm going to mark in green. We use this for values x less than or equal to 2. So we're going to use that expression for all of those values. And we're going to use this expression right here. Oh, they're kind of close together. Let's do something that are not close together. Let's do orange. Haven't done orange yet. And we use this expression for values that are greater than 2. Okay? So 1's right here. In fact, let's mark it on the little chart. Here's 1 right there. 1 we're plugging into the top equation because 1 is less than or equal to 2. So we plug 1 into that, so we get 3. Subtract 1 is 2. That was simple enough. All right, problem number 9. This time we are plugging in 3. Well, on our little chart up here, 3 lands right about here, so that's where 3 is. 3 is going to be our orange equation because 3 is greater than 2. So we're going to plug 3 into this equation right here. So we get 3 divided by 2 minus 1. So 3 divided by 2 is 1.5, if you want to think of it that way, or we could change this into a fraction, doesn't matter. So we get 1.5 subtract 1 is 0.5. Answer is B again. And problem number 10, what is the value of the limit as x approaches 2? Okay, so as we look at our little number line up here, we want to know what's happening, where's our y value as x gets closer to 2 from the left, and as x gets closer to 2 from the right. So the left, we're going to be using the top equation. Okay, so we're going to evaluate the limit as x approaches 2, the limit as x approaches 2 from the left of our function. Okay, so that's using the top equation, so I plug 2 into that. 3 subtract 2 is, oops, that's not a negative, that's a, sorry, 3 subtract 2 is 1. Okay, so that's our left limit. Our right limit, as we can see, we're using the orange equation. These are for values greater than 2. We get, we're plugging in 2, right? Yeah. So we get 2, sorry, the limit as x approaches 2 from the right. We'll plug 2 right into this equation. We get 2 divided by 2 minus 1. That's 1. Minus 1 is 0. Okay? So the left limit is 1. The right limit is 0, which means that the two-sided limit, okay, that's what we're looking for. The two-sided limit doesn't exist. They're not going to the same place. So the answer to this one is does not exist. All right, let's take a look. 11 through 15. All right, use the following graph of f to answer questions 11 through 15. Problem number 11 says, evaluate f at negative 2. So plug in negative 2, and what do we get out? So let's find negative 2. Here's x value of negative 2. As we go up, we see that's a hollow dot, so we don't want that one. As we come down, though, there's our solid dot, and the y value of that point is negative 1. So 11, the answer is negative 1. Okay, problem number 12. This time we're looking for the limit of f as x approaches 1. So we come over here, here's 1. Now remember, we're looking for the limit, so I don't actually care what's happening at 1. I care what it looks like is happening at 1, which means like what's happening from the left, what's happening from the right. So as we follow this side guy right here, as x approaches 1 from the left, my y value is approaching positive 3. So the left limit is 3. The right limit, kind of follow this guy around, as it approaches 1 from the right, my y value is also approaching 3. So the limit does exist. The left limit's going to 3, the right limit's going to 3, and so our two-sided limit in this case is 3. Notice that I didn't care that you can see that the actual value here, if I plug in 1, is positive 1. But I don't care about the actual value. I just care about what the limit is. Like if you could not see what was happening at 1, what would you guess the answer would be? If you plugged 1 in, the answer to that would be 3. All right, problem number 13. We are looking for the limit as x approaches 3, positive 3, from the left. So this time we only care about the left. So here's positive 3. As we come at it from the left, okay, as we come at it from the left, what are we getting closer to? So we come at it from the left, and we are getting closer to a y value of negative 2. Okay, it just so happens that this limit actually does exist, but that's okay. I mean, I bet I meant to have that be positive 5. So just for kicks and giggles, let's just look at positive 5 really quick. So if I came at positive 5 from the left, my answer would have been negative 3. If I came at positive 5 from the right, my answer would have been negative 1. You can see those two values are different. So the limit at 5 doesn't exist. But that doesn't have anything to do with problem number 13. That just has everything to do with what I think I meant to put there. But that's okay. Moving on. All right. The limit of f of x as x approaches negative 2 from the right. So here's negative 2 right here. So as we come at it from this direction, we're following this part of our function right here. Okay, so as x approaches negative 2, what is my y value getting closer to? Well, we're coming down, coming down, coming down, then we hit 1, and we just stay at 1, 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 until we get closer and closer to that point. So our y value, in this case, is positive 1. Notice that we came at it from the right, not the left, came at it from the right, because of that plus sign right there. All right, problem number 15. List all values of x. Okay, all values of x for which function f is undefined all values of x for which f is undefined. I just noticed that my thing's messed up. There we go. We weren't even staying on the page. There we go. Anyways, list all values of x for which f is undefined. All right, so let's see. That means that we're not going to have any outputs for those x values. So as I come around here, because of my graph here, I know I have outputs for all of these x values. So here's my first little test right here. -2. Do I have an output at -2? And I look up because there's not one. But I look down and yes, there is a point defined on -2. So he is defined. These are all, this is all continuous right here. So they're all defined. So we're good there. Okay, here at +1 is my next little problem. If I plug in -1, notice I have a hole up here, but I do have a point defined at 1. So +1 is okay. Follow this line around. Okay, here at 2, I have an asymptote. If I plug in 2, we know it's coming up. I don't see a point defined there. Coming down, I don't see a point defined there either, which means x at f of 2. So if I tried plugging 2 into my function, it's going to be undefined. There's no answer there. So x equals 2. That's a problem. He is undefined. X equals 2 is undefined. Let's keep going. So I follow this guy around. He's continuous, so he's good. Here's my next problem I want to look at. 3. If I plug in 3, notice I don't have anything defined. So 3 is also a problem. Okay, moving on. Here's my next problem, 5. So if I plug in 5, I've got a hole here and a hole here. Or I should say just not defined there. It's not really a hole. But it is defined right here at -2. So I do get out an answer for 5. So he's okay. And then because this is continuous all the way through there, I'm good to go. Notice that all this I've had students in the past wonder, what the heck does this mean right here? This is just interval notation. It's just saying, hey, for x values from -5 to +6, okay, where's the function undefined? And I have the bracket, so I mean I could include -5 and I would include +6. So that's what this means. It's just like, hey, in this little window right here, where is my function undefined at? That's what that notation means right there. And we know it's an interval because it says interval. All right, almost there. Problems 16 and 17 says identify any vertical and horizontal asymptotes of the following functions. So let's start with 16. Now we know when we're trying to find vertical asymptotes, let's do horizontal first. Horizontal asymptotes, we have basically 3 things that could happen. Asymptotes. Okay. Notice we are dealing with polynomials on top of polynomials. So here we go. So case 1. In fact, let me just scroll up here so we have enough so I can make sure I'm not going to run out of accidentally right off the screen. So we have, case 1. No horizontal asymptote. And what happens with this is we're going to, the numerator, the degree of the numerator is larger than the degree of denominator. Okay, so that would happen there. So for example, if I had something like x cubed plus 1 divided by x minus 8 or something like that. The degree on the top is 3, the degree on the bottom is 1, so the top is going to grow faster than the bottom, and so therefore we would have a no horizontal asymptote. This thing would be growing or decreasing without bound. Okay, so that's case 1. Case 2, I didn't really give myself very much room, did I? Case 2, we could have a horizontal asymptote at y equals some number, well, we'll call it some number c, where c is not 0. Okay, so some number other than 0. Okay, case 3 is going to be when y is equal to 0. So case 2 occurs, so here's my example. Case 2 occurs when the degree on top, okay, is greater than the degree on the bottom. So, sorry, I'm just looking at how this was not a very good way of explaining this. This I'm telling you what's happening. This I'm just telling you how to find it. It's not exactly flowing, is it? But that's okay. It's when the degree on the top So the degree of the numerator is equal to, so degree of numerator is equal to the degree of the denominator. Okay, that's when you're going to have this kind of asymptote. So for example, if I have 3x squared plus 1 divided by x squared minus 18 or something weird like that. Okay, notice that the degree on top is 2, the degree on the bottom is 2. This would have a horizontal asymptote. Okay, the way we'd find it is we'd ignore everything but the leading terms and we'd simplify. So this one would have a horizontal asymptote at 3. Does that make sense? And then finally we'd have case 3. Let me just write it down here. Case 3. Okay, this is a horizontal asymptote at y equals 0. And this occurs when the degree of the numerator is less than the degree of the denominator. So for example, if I have x minus 1 over x squared plus 5, something like that. The degree on top is smaller than the degree on the bottom. It doesn't matter how much smaller, it just has to be smaller. This thing is going to go to 0. Okay, so those are our horizontal asymptotes. Okay, vertical asymptotes. So we're already started over here. So vertical asymptotes occur when you have some number divided by 0. That number, I guess I should probably just stick with the same notation I was using before. Let's call it C. Some value divided by 0, where C, that constant value, is not 0. Okay, that's how you get vertical asymptotes. All right, let's start with horizontal asymptote on problem number 16. So we can look at this and we can say, okay, look, the degree on the top, this is a degree 3 polynomial in the numerator. The denominator has a degree 2 polynomial. So which case does this fall under? Falls under number 1. The degree of the numerator is larger than the degree of the, what is this, degree of the denominator. So this one has no horizontal asymptote. Right? It's going to just increase or decrease without bound. It might have an asymptote, but it's going to be a quadratic or a cubic or something like that. It is not a horizontal asymptote. Case 2 and case 3 is when you get horizontal asymptotes. So 16 has no horizontal asymptote. Now let's take a look at vertical asymptotes. Probably the best way to figure this out is to factor everything that you possibly can. So on the top, in fact, let me rewrite this. We have x cubed plus 2x squared minus 3x. On the bottom, we have x squared plus x minus 2. So the top, it's a little equal, it's like a little arrow. It's not a smiley face, it's an arrow. So on the top, I factor out that x. Left with x squared plus 2x minus 3. And on the bottom, we've got x squared plus x minus 2. So we have this quadratic on the numerator and the quadratic on the denominator we can factor still. So I've got that x. This quadratic factors to be x plus 3, x minus 1. And this quadratic down here factors to be x plus 2x minus 1. Okay, so that's how it factors. So let's see. Vertical asymptote occurs when we end up dividing by 0. So let's see all of our potential candidates. So possible vertical asymptotes are x equals -2. That will cause the whole thing to go to 0 in the denominator. And so will x equals +1. Okay. Let's just check the -2. If I plug -2 into any of these terms up here, any of these expressions up here, I am not going to end up getting 0. So I'm going to get some constant divided by 0. So x equals -2 is a vertical asymptote. So we have a vertical asymptote definitely at x equals -2. Let's take a look at x equals 1. X equals 1 will make the denominator equal 0, but notice right here it will also make the numerator equal to 0. In fact, those will cancel out. So x equals 1 is not an asymptote, it's a whole. So we only have one vertical asymptote. So vertical asymptote is x equals -2, and we have no horizontal asymptotes for problem number 16. All right, problem number 17. Once again, let's start with the horizontal asymptote. Let's see, so we have these three cases. Let's see what we got going on in 17. We have the degree of the numerator, so it's a degree 2, divided by another degree 2. So they have the same degree. So that occurs, that's that case 2. So we will have a horizontal asymptote. It will not be at 0, it will be at someplace else. And to evaluate that, what we do is we look at the leading terms, and if there was a negative out front, we include that negative. So we got 4x squared divided by 2x squared. Well, the x squareds cancel out, and 4 divided by 2 is 2. So we have a horizontal asymptote at y equals 2. So 17, horizontal asymptote at y equals 2. All right, so to find the vertical asymptote, we need a factor. So let's factor this sucker. The top, notice I can pull out a 2. Make things a little bit easier. So I got 2x squared minus 2x minus 3. On the bottom, I can factor out an x. So that leaves me with 2x plus 1. The top, let's factor that now. 2x squared minus 2x minus 3. If you look at this and try to, whichever method you try working out, you're going to find out that this actually is not factorable. You cannot factor this. So actually, this is as far as we know. Whoa, that's not what I meant to do. So the numerator is as factored as we can possibly get it, and the denominator is also now factored as much as we can possibly get it. So let's see what makes the bottom equal to 0. X equals 0. Is a potential, we'll call it a possible vertical asymptote at x equals 0. We also have this guy right here, 2x plus 1. So when does 2x plus 1 equal 0? So let's just do this in green. 2x plus 1. When does that equal 0? We're going to subtract 1 from both sides, and we're going to divide by 2. So we get x equals a negative 1/2. That's another possible vertical asymptote. Okay. As we look in the numerator, well, we can see that neither of these is going to make the numerator go to the 0. And I can tell that straight from, from this quadratic right here. It's not factorable, so which means that we are not going to be able to break this down any further and get an x all by itself or a 2x plus 1 all by itself. If that were the case, it would be factorable. So, yeah, those are going to be our vertical asymptotes. They do not make the top equal to 0, they just make the bottom equal to 0. So we have vertical asymptotes at x equals 0 and x equals negative 1/2. Okay, our final problem on this review is problem number 18, which says, let f be a continuous function such that if you plugged 5 into f, you'd get 2, and if you plug 2 into f, you get 5. Let h of x, so some completely different function, h of x equal whatever our output is for f when we plug an x value in, minus that same x value. Okay, is there a value r for between 2 and 5 such that if you plug that value into h, you get out negative 1? Okay. Hopefully when you look at this, kind of gives you an idea of what we want to do here. We want to use the intermediate value theorem. Okay, so now the intermediate values theorem essentially says this. If you've got some function, in this case, which function are we looking at? Let's make sure we use the right notation here. We're not looking at function f. We are actually concerned about function h. Okay, so if h, and there's two things that h has to be true with h to use the intermediate value theorem. If h is continuous, okay, on our interval, our closed interval, so 2 to 5, and h of the value that we're trying to plug in, the value, our desired value if you want, which in this case is r, and h of r is between our two endpoints when they evaluated h, so between h of 2 and h of 5. If these two things are true, then we know that we have to hit every y value between those. Okay, if that's true. So I'm not even going to put the then. So let's kind of see what's going on here. Let's see if we can figure this out. We're going to draw a picture of H. Okay, let's draw a picture of what H looks like. So H, here's what H is going to look like. 1, 2, 3, 4, 5. Okay, so let's see if H is continuous on 2 to 5. So let's see what's happening at 2. If I plug 2 into H, so where is my H? Here's my H right here. So let me just rewrite this equation. So we have H of X is equal to F of X minus X. So we're going to plug 2 into that and see what happens. So we get H of 2 is equal to F of 2 minus 2. Well, F of 2, we know from the directions up here that F of 2 is equal to 5. So H of 2 is equal to 5 subtract 2. So H of 2 is equal to 3. So we know if we plug 2 in, we get 1, 2, 3. We get 3 out. Okay, we know that's for sure. There's something we know about H. Let's see what happens at the other endpoints. Let's plug in 5. So H of 5 is equal to F of 5. Whoops, that's supposed to be a 5. Sorry. F of 5 minus 5. And we know that H of 5, so F of 5 we know is 2 right here. We can see it right there. If I plug in 5 into function F, I get out an answer of 2. So 2 subtract 5. So H of 5 is equal to negative 3. So here's 5. Let's put some tick marks down here. 1, 2, 3. Okay, so we know at 5 it is negative 3. So let's take a look at this. So we know that H of 2 it's positive 3, H of 5 it's negative 3. Question is H continuous? Well, if we look at this, this is how H is defined right here, right there. And it's made up of 2 terms. X is a continuous function. The question is F a continuous function? And as we read the directions, we see, yeah, F is a continuous function. So since H is just an addition problem between 2 continuous functions, H is definitely going to be continuous. So as we know that H is continuous between 2 and 5, the question is there some value between 2 and 5 that will give me out a value of negative 1? In other words, do I have to touch that line at least once to connect those 2 dots? And the answer is yes. And so our answer will look something like this. Since H is continuous from 2 to 5, and H of R, in this case H of R, so negative 1, so we can actually erase that, and negative 1, whoops, get back on that, and negative 1 is between H of 2, which is 3, so I'm just going to cross that off and put 3, and H of 5, negative 3. There must be some R in that interval such that H of R is equal to negative 1 by the intermediate value theorem. So something like that. Some answers sort of like that. And that does it.